Morning, guys. So yesterday we had a look at a guy called empirical formula. That was the harder way of asking the question, where experimentally we're actually given the relative proportions, the relative masses that they find in some unknown sample. And what we want to do is we want to convert that mass information, that percentage composition information, to get back to what's called the empirical formula. Empirical formula is the simplest whole number ratio. What compound would actually represent the proportions that we actually got? So let's just try for a quick practice here. It's a very systematic procedure of looking for an empirical formula. I want you to find the empirical formula for a species containing, remember species just means substance, okay, containing 77.9% iodine and 22.1% the remainder is oxygen. So again, they've done the hard work. They've done the experiment. They've actually punched it through some machine, and they figured out, okay, a good 3/4 of this is actually the iodine element. 22.1% is the remainder is oxygen. I want something like IXOY. I want to know the numbers. I101, I105. I want to know the relative, the simplified proportions. So just like our very last question from yesterday, we're going to start off assuming we have 100 grams. You can always pause the video and try it out for yourself as well. Assume we have 100 because percent works really nicely with 100. Imagine 77.9 grams is actually iodine. Remember, iodine by itself would have been I2. This isn't iodine by itself. So just when I divide molar mass, just a molar mass of 1 I. On the other side here, we have 22.1 grams. Again, for oxygen here, we're going to set up a row here for iodine. We have 77.9 grams. Oxygen is 22.1 grams. You see that we've actually been able to convert percentage over to mass, no problem. And now we're ready to do our steps. Let's divide up the mass. Iodine here has a molar mass. Double check my numbers. I'm getting 126.90. Oxygen has a molar mass of 16. So 77.9 divided by 126.9 gives me here 0.6139. 22.1 divided by 16. Keep a few extra decimals so you don't accumulate any rounding errors, and we're going to eventually round to one whole number anyways. This one here is actually moles. Now, I could say I 0.6 to oxygen 1.3 like that. It's not easy to look at, so what we're going to do is we're just going to divide the smallest number. Let's rescale it. The smallest number this time is the 0.6139. Let's rescale everything by this 0.6139. The top number becomes 1. The other number divided by 6139. This gives me, give or take, 2.25. Right? Again, remember you do a judgment call here. In math class, 2.25 to 2, that's not that much rounding. But in this empirical formula stuff here, I don't want to do crazy rounding for one element in case it skews the ratio. Oh, I noticed this one here to be 1/4. What if I just scaled everything up by 4? I made the I4, 2.25 times 4 is actually 9. So we actually get I409. That's now a simplified ratio. That's now the compound. That's the empirical formula that we need. All right? So hopefully you get some practice with that over the worksheet here. We are still going to have to practice this. It's just that our IB is never so nice to us. It never simply gives us, oh, here's a percentage, and now you're ready to do this. I'm going to write for you a question sort of the IB style, how they're going to word it. We will eventually need to do this work, but it's going to take us a little work to actually get to these first starting numbers. So I want you to compare this setup as shown, compare it to the new stuff we did today here. So how does IB word this empirical formula question? Just steal one of their questions here. 2.80 grams of hydrocarbon. Remember CXHY. Are combusted. Okay, we put it through a burning reaction. Are combusted to produce 8.80 grams of carbon dioxide, right? Burning produces CO2, and 3.60 grams of water. Right. The question is find the empirical formula. Right. We're already scared away. Right. With the exception of that last part here, find the empirical formula. It's weird. First thing, they're not giving us percentages; they're giving us masses. Now we've seen masses before. But now suddenly they give us a burning reaction, huh? And now they're giving masses of a couple different things, and now they're still asking for the empirical formula just this one. I'm confused. whenever you're confused like this here, see if you can sketch out the question. See if you can sort of analyze the problem, draw pictures if you can. In this case here, we're told it runs through a combustion. So imagine taking a CXHY. We are still interested in the empirical form of this. I actually have 2.80 grams. Try to convert the word equation to something that I know. It's run through a combustion reaction and it produces CO2, 8.80 grams of it, and it produces water, 3.60 grams of it. Right? So at least I've been able to translate some of those numbers there. Now, when you look at those numbers, at first you'd be like, uh-oh, something's off. Right? Conservation mass, it doesn't agree anymore. I'm only putting in 2.8 grams, and later on I have some 12, 13 grams or so. Where did all the extra mass come from? What else do we need for a combustion reaction? Oh, right. We need oxygen here. They're just not telling us how much oxygen there is. Usually the terminology that we have for that here is, assume we have an excess of oxygen. There's a ton of oxygen. It's not going to affect our measurements, but there is enough oxygen. In this case here, if you like, you could have found the total mass of products. If you minus off this, you can actually figure out how much oxygen is actually reacted. So at least that ensures that mass is conserved. But still, we need some percentage data for the hydrocarbon to actually figure out what the empirical formula should be. The reason why they always ask you this in terms of a combustion reaction is it really nicely separates the carbon. The carbon ends up just in the carbon dioxide, and the hydrogen just ends up in the water. So that's going to actually help me give me my proportions of C's and H's separately, and that way I can do the empirical formula stuff from there on in. You'll also find that because I don't know the empirical formula that I have right now, I can't balance this equation. However, the whole notion, the whole idea behind balancing was the fact that any carbons that I have at the end of the day had to have come from the carbon source. Any hydrogens that I have at the end of the day have to all be accounted for. Every atom has to have come from a hydrocarbon as well. So even without the ability to balance, I can actually figure out, if you can tell me how much carbon I have here, I know all that carbon came from the CX. If you can tell me how much hydrogen is here, sure, working out that H2O ratio and whatnot, I know all that hydrogen had to come from here. So maybe I'll write this down in words for you here. Although we cannot balance, since we don't know the EF, the empirical formula yet, okay, all the carbon had to come from the CXHY, and in a similar fashion, all the hydrogen had to come from the CXHY. So although we're not able to actually put coefficients and make sure the number of atoms on the left matches up the number of atoms on the right, I can still say the only reason why I would have C had to come from here, the only reason why I had H had to come from here. The oxygens are a little more problematic because those excess oxygens I don't really care about, that oxygen actually goes into the other two as well. So I'm going to show you one nice way of doing this here. I'm interested then in figuring out how many grams inside my carbon dioxide. I know I had 8.80, but I know that's carbon dioxide. That's not just carbon. So what I'm going to do here to find how many grams of carbon in 8.80 grams of CO2 shouldn't really surprise you. I'm going to take 8.80 grams. That's the total CO2 product. And what I'm going to do is I'm actually going to do it by proportion. I'm going to figure out, well, I know carbon's mass and I know carbon dioxide's mass. This guy here is actually going to be a percent. This is why we did this yesterday. This is a percent composition of carbon in CO2. Right, we actually totally did this math yesterday. But what I'm saying here is, if you just work through the math with me, if we have 8.80 grams, that's my total product. If the carbon part of it is a molar mass of 12.01, the whole molar mass is 44.01. We had said it was about 27%. If I know in total I produce 8.80 grams of carbon dioxide, and I know some 27% by mass is actually carbon, I can actually figure out what is that 27% on this 8.80, and this actually finds for me 2.40 grams is actually carbon. So what I'm picturing there is, in my sample, I have 8.80 grams, and there are all these blobs of CO2. But what I did is well, for carbon, out of this compound here, carbon makes up about 27% or so. So if you have 8.80 grams total of these molecules, and just focusing on the carbon part of this compound, if I take 27%, I'm getting about 2.4 grams. That's the carbon part in the carbon dioxide. Again, I'm not chemically coming in and actually destroying the molecule and actually separating the bonds. I'm just trying to figure out what the carbon source is. That's definitely one way of doing it. I'll show you how that would happen if you do it on the water side as well. You could, in a similar fashion, go, how many grams of water are there? Well, let's take water's mass. This time I produce 3.60 grams of water. For water, there's actually 2 H's in H2O. So you could punch it through here. 3.60 grams of total water. 2 times 1.01. The total molar mass is 18.02. Let's figure out by mass. 3.6 times 2.02 divided 18.02. This gives me 0.404 grams of hydrogen are actually formed. There were actually a couple different ways you could have found that number. Don't lose sight of this one here. I know the whole thing was 2.80. After the first calculation, I realized 2.40 grams is C. If the whole thing was just made out of C's and H's, I know very well the rest of it should be 2.8 minus 2.4. It should be 0.40, which I do verify here. So far we have the percentage composition way of solving it. You can just do it by a difference of mass at the beginning way of solving it. There's actually one additional way of solving it. This will get us a little bit into the stoichiometry that we'll see later on in the chapter. But with stoichiometry here, I'm just going to do it just right up and down from here. What I am interested in is actually the grams of hydrogen. You don't have to do all these ways, by the way. Just do just one way. I'm starting with 3.60 grams of water. This gets us into stoichiometry because we're actually given a mass of a chemical, but we're interested in actually jumping to a mass of a totally different chemical. We're asked to jump from one thing to another thing. There is no easy way of doing it. In this case, your percentage composition was an easy way. What we'll actually need to do is we'll get into all these conversions. We'll divide out the molar mass of water. Let's compare it to sort of numbers, boxes of water first. And then we can say for every one box of H2O, how many boxes of individual H's would I count? Well, for every water molecule, I actually have 2 H's. If I have one box full of waters, I actually have 2 H's. And in the end, you want grams back. So moles to 1.01. Don't worry, we're going to do all of this in a later lesson. I just wanted to show it to you here because mathematically, this is actually what you did. We took 5.60. When you multiply it, this guy here is actually the percentage H in water. That percentage composition has factored in the 2 multiplied by the 1.01 divided by the 18.02. It's done all the work for you, but it's just sort of a little bit scarier in terms of unit conversions. We're going to slowly work our way to this sort of stoichiometric method, but just treat this for now. It's the third way of doing it. You can totally do it just with that percentage composition. Just somehow find the C and find the H. That's already hard, right? It's already a lot of work. And now at this point, this now looks like our familiar question. I now have 2.4 is carbon, 0.4 is hydrogen. Now I divide out the mass. Now I divide out the smallest one. Now I'm ready to do all this other math that we're used to. So a lot more work to actually get to those starting numbers here. Let's see what we get then. So set up a row for carbon. 2.40 grams is that. Hydrogen, we found 3 different methods. 0.40. I'm going to divide out the molar mass first. Divide out the M. Carbon has a molar mass of 12.01. Hydrogen has a molar mass of 1.01. 2.4 divided by 12.01. You can be a little sloppy with sig figs. This is giving me 0.1998. 0.4 divided by 1.01 gives me here 0.396, right? So those are technically the ratios already. They're just not so nice to look at. How do we start simplifying it? Is we divide out the smallest one. The smallest number so far is the 0.1998. So let's divide out both things by 0.1998. This one practically drops to 1. Take the other one, divide it by 0.1998. I'm getting 1.98. So I know in general I want to keep my rounding to a minimal, but that's not that bad rounding. Let's just round that to 2. So there we have it. We did a lot of work to actually find these starting numbers. Then the rest of it was pretty systematic. And now we figured out for every one C, there's actually 2 H's. This is no doubt, this is called the empirical formula. This is the simplest whole number ratio that represents the proportions that you found experimentally. What if I came along and added one step? I already added one step here. What if they don't give you the numbers to begin with? You actually need to go and find the numbers. I did the work that we're used to, divide out the mass, divide out the smallest one. And now we can actually tack on one other step. What if I told you this compound doesn't exist? You say, great, right? I went through all this work and now you're telling me somehow this is wrong? It's actually correct in the sense that this is the empirical formula. The simplest ratio is C1H2. How do I know this compound doesn't exist here? We'll do a lot of this here in our bonding chapter. Carbon actually has 4 valence electrons. It could potentially make 4 bonds. So far you have carbon making 2 attachments. That would stabilize those 2 unpaired electrons here. Having these 2 unpaired electrons would make carbon what's referred to as a radical. And radicals are super unstable. Radicals are very high energy. They're very unstable. They don't exist for very long. So that's how I know this compound actually doesn't exist. Well, what's the problem here, right? Why did experimentally this happen, right? Well, the problem is actually in the definition. If you look back at the empirical formula definition, empirical formula had that notion, it's the simplest whole number ratio. It's been simplified. That means if this is a fraction, this is a ratio, could I actually be the compound, let's say C2H4? Well, sure. If I simplify that, that would be C1H2. Could I really be the compound C3H6? Well, sure, I could be that one, right? As long as the ratio says for every 1 carbon that I have, I actually have twice the number of hydrogens, all of these ones, and even bigger, all of them will share the same empirical formula. And here's sort of our last step, one last little addition we can do to a problem here. We now call this one here the molecular formula. We haven't seen this before. So molecular formula, the MF, the molecular formula is the numbers in the actual compound. So if my empirical formula, it was good in a way because it's simplified, it made the numbers look pretty, but because the molecular formula here is going to be some multiple, right? It's some, like if you imagine the empirical formula to be a Lego block, I may have 2 of these Lego blocks together, or 3 Lego blocks, or 4 Lego blocks. My molecular formula may actually be a scaled up version. What we're going to treat here is our molecular formula will always be a multiple of your empirical formula, empirical unit. So what's really nice about this here is it's going to be a multiple of the empirical mass as well. Mass is something really easy I can measure. This guy's molar mass here, carbon is give or take 12, hydrogen is give or take 2. This one weighs about 14. Although the empirical formula for C2H4 is also CH2, that means the percentage composition is also different, but the mass is 28. The mass here is 42. Right? The mass is just going to be some scaled up version depending on how many Lego blocks I have. If you like math, you can say, well, what is this factor here? You can take the molecular mass or molar mass, take the mass of the entire compound, divide out the mass of the Lego block. Divide out what I'm calling the empirical mass. So this 14 here is called the empirical mass. It's like doing a molar mass on your empirical unit. It's like saying your Lego piece weighs 14. If I now tell you, they actually need to give you some experimental data, if the actual M is, let's say, 42, all you would do is you'd say, okay, 42 divided by, well, each Lego block weighs 14. How many Lego pieces? Well, 3 Lego pieces. If I have 3 of these CH2 blobs together, I'm going to have the compound C3H6. And this is the one time, yes, I'm saying we have 3 Lego pieces, C1H2. Normally, once you find these subscripts, those are set. You can't change them ever again. But this time, I actually have 3 Lego pieces, so 3 of these blobs together. So as a covalent compound, I actually have 3 carbons, and I actually have 6 hydrogens. What's the difference between having the 3 scaled in like that versus 3 as a coefficient? As a coefficient, it's saying my molecule is CH2. I actually have 3 individual blobs of CH2. What we're doing here is we're actually saying, nope, the whole molecule is actually 3 CH2s altogether. It's actually a C3H6. So that is now called your molecular formula. That is now just one small little addition, and all we really needed was, what is the real molar mass? They either come right up front and say, oh, by the way, the molar mass is this, or they give you enough experimental data to actually get this number. So I'm going to do one quick question just to show you that little bit, and then I'm going to give you an old paper 2 question just so that you get used to the wording and also see sort of the level of detail that IB expects. So first question first, just introducing to you, if they don't quite give you the molar mass, how could you find it? Let's find here 1.60 grams of gas at STP occupies 350 milliliters, given the empirical formula. So they've done a lot of the hard part for you. Given the empirical formula is POF3, so phosphorus, oxygen, and 3 fluorines, that's your Lego piece. I want you to find, this time, find for me the actual compound. Don't just give me the simplified ratio. Tell me, is it 1 Lego block? Is it 2 Lego blocks? How many Lego blocks there are? So let's see if we can take it apart here. So they've already given you your Lego block. This is your empirical formula. Because we are going to need the mass of your Lego piece here, let's go to our periodic table and let's just go and add up. What is phosphorus mass? 30.97. Again, like I said, I don't normally show this. Plus 16, plus 3 times fluorine. You should be able to find for me that the empirical mass, each Lego piece weighs about 104 grams or so, give or take. This is experimental anyways, there's going to be some rounding. These questions are always a little bit confusing because there's no one right way of doing it. All I can hint towards here is we know our molecular formula is going to be some scaled up version. It's going to be some whole number unit of your empirical formula. What we're going to need to do to make a comparison is we're going to do whatever we can to try to find molecular mass. And here's some dimensional analysis will actually help us out. Molecular mass will be grams per mole. It's like molar mass, but it's the molar mass of your actual compound. So you're going to do whatever you can using the numbers given. They didn't say, oh, by the way, the molar mass is this time. This time they gave you, oh, great, they gave me a grams, so they gave me this top number. You're going to do whatever you can to get grams on top and get a moles on the bottom. That way I can divide them. That way I can figure out how heavy is my real compound and then figure out how many Lego pieces weighing 103 would actually weigh that. So they give me that mass. Unfortunately, they don't give me the moles yet. However, they do tell me that this volume, sorry, I meant to do a highlight here. This volume is actually a gas at STP. What other conversion do we know for a gas at STP? Hopefully you're able to remember. 1 mole is actually 22.7 decimeter cube. As long as I'm at this special temperature, special pressure, my conversion factor is 22.7. So what I'm saying here is I can try to do my best and actually get grams on top, moles on bottom. Let's first find moles. I have 350 milliliters. I'm going to convert that to liters right away because I know I want liters for my conversion. 0.35 liters. I know it's 22.7. You can even say liters in your conversion. 1 liter is a decimeter cube. 0.35 divided by 22.7 gives me 0.0154. So not a whole lot. I need about 20 liters for a box, an Avogadro number full. I only have a little bit under half, 0.35, right? Not even full 20. So I have about 1% of a box. But so be it. I've now accomplished it. My real gas is 1.60 grams on top. I figured out that inside the balloon are these 0.0154 moles. By dividing the two of them, it just rescales it for me. If 1.6 grams for 0.0154 moles, if I actually have 1 whole mole, what's the real molar mass? I'm getting 103.77 grams per mole. And depending on the question, sometimes they'll give it to you as a volume, sometimes they'll give it to you as moles straight away. You just do whatever you can to get grams on top, moles on the bottom. So now we're ready to finish the question. We can say, all right, so if the real compound, given the experimental numbers, if the real compound weighs 103 and the empirical formula weighs 103, it won't be exact, right? But in this case here, we're saying, oh, maybe my molecular formula is just 1 Lego block. This time your molecular formula is also POF3. Just to show you that, yes, molecular formula might be a scaled up version. Many times your empirical formula is actually your molecular formula already. Right. I'm going to show you one other way of just showing this work here. Again, our hint, I'm just going to write this down in words for you. Try to get grams on top and moles on bottom. That's the only thing that remains consistent as we go through here. I could have actually done this work here all in one step. I could have said, well, if I'm interested in finding the real molar mass grams per mole, they gave me 1.60 grams. They didn't quite give me moles. They gave me liters. So I can say 1.60 grams, the volume was 350. So again, I'm going to convert that to liters, 0.35 liters. What conversion factor would I need to get rid of the liters and actually get to moles? Well, liters is on the bottom. Liters needs to go on top. I need to pick up a mole. That way the top unit cancels the bottom unit. And here you can actually see 1 mole is 22.7. If you follow through that math there, it does exactly the same thing. What I had done previously is I had done just the 0.35. I had done the divide the 2.75. I had done just this bottom part. And then I did 1.6 divided by this answer. This one here does it all at once. The reason why I word it this way here is sometimes they even word it to you as a density. Density here actually has units gram per liter, and in that case there, how do you get gram per liter over to gram per mole? You just use molar volume. So again, that part, sometimes it's a little surprising with what information they actually give you, but you just do whatever you can, try to get grams on top and moles on bottom so that they cancel out. Right? So let me just ask you one final question that introduces all of this together. This was an old exam question, so make sure you're comfortable doing this. So we'll do this as our vitamin C question. 1 gram of vitamin C. Vitamin C has a compound CXHYOZ. 1 gram of this vitamin C, they actually matched up with the real vitamin C, so the numbers are actually correct here. They burn it again, burn to form 1.50 grams of CO2 and 0.408 grams of H2O. What is the molecular formula? What's the real compound, scaled up or not scaled up? What's the real formula given the molecular mass? So they're helping you out this time. Oh, the real compound actually has a molar mass is 176. And you'll notice that when they give you that number here, they actually say it to you without units. That's the way we like it, because this one here is relative, right? So no units because it's relative to carbon 12, right? So I would pause this video here, see if you can try out the question, see where you get stuck, and then you can come back and have a look. What I would do at first is I would just start off with a picture. I'd say, well, I'm starting off with a compound CXHYOZ. I don't actually know what that compound is. Right? I don't know the numbers, so I can't balance it. However, I do know we have 1 gram worth. That's going to become important later. I know there is a burning reaction, so I know it's actually reacting with oxygen. That scared me away last time, doesn't scare me away this time. I assume the combustion is complete, so I assume we end up with full CO2 and full water. And again, I'm given numbers 1.50 grams of carbon dioxide, and I'm getting 0.408 grams of water. Notice that depending on the question, the starting amount that's burning will be different. Even the starting amount, ending amount of carbon dioxide and water will be actually different, but your method will still be the same. Our goal is going to be, let's figure out where all the carbon went. Well, the carbon went to CO2, regardless if I can balance or not. The hydrogen, in a similar fashion here, hydrogen likewise goes to hydrogen. So those two are really easy. You can just use percent composition of carbon, percent composition of hydrogen. You can get those numbers. The question here is, our vitamin C actually has some oxygen source as well. The oxygen ends up in 2 compounds. You could hypothetically say, well, whatever's not carbon, that's oxygen here, and that's oxygen here. You could add up, well, these are all O atoms. Why isn't that all oxygen? It is all oxygen. Unfortunately, if you look back, where did the oxygen come from? Some of it came from the vitamin C that I want, but a lot of the oxygen is actually going to come from excess oxygen. That was just my other ingredient. I wouldn't actually be able to find the grams of oxygen just in vitamin C with my current technique. So again, I can pause there. You can think about how you're going to do it. All right, so let's try it out here. Let's find how many grams of carbon. Again, the easiest way of doing this is using percent composition. This time it's 1.50. That was different from earlier. My carbon dioxide, carbon has a mass of 12.01. The whole mass is 44.01. So 1.5 times 12.01 divided 44.01. This gives me 0.4093. You can be a little more sloppy with sig figs because ultimately I'm going to round to 1 digit. Let's do a similar calculation with hydrogen. For this one earlier, we could do a subtraction from the 1 gram. This time we can't just yet because we also have oxygen. We'll do that as our last step actually. This time I'll either use the stoichiometry way, we'll see later on, or better yet, just use the percent composition. Every hydrogen weighs 1.01. I have 2 of them, divided by 18.02. 0.408 times 2.02 divided by 18.02. The hydrogen part of this is 0.04574. I know all the hydrogen had to come from here, so I now know the carbon and the hydrogen part. We had said we had a problem with oxygen because not only did the oxygen end up in two places, most of the oxygen was actually excess oxygen that we actually didn't care about. I actually just want to know from an empirical formula, what's the O part in my compound? And here's where just conservation math saves the day here. If I know the vitamin C I burnt was 1 gram, if I minus off the 0.4093 that I know to be carbon, and I minus off the 0.04574 that I know to be hydrogen, what's left over is definitely going to be oxygen, and just the oxygen I want. So 1 minus 0.4093 minus 0.4574. Double check my numbers. I'm getting 0.54496. Right. That is oxygen that's purely to my compound, not the excess oxygen. If you did percent composition on this side here and you found out the total oxygen, that wouldn't just be this 0.544 number, because that would contain a lot of the extra oxygen. We end up with a total of about 1.9 or so, maybe as well 0.3, 0.9 grams or so. But now we have the numbers. At long last, we have sort of our starting point, and we can now set up our rows. Carbon is 0.4093 grams. Hydrogen is 0.04574 grams. The oxygen that we care about, that's in the vitamin C, 0.54496. At this point, you can do your very systematic steps here. Let's divide out the mass. Carbon weighs 12.01. Hydrogen weighs 1.01. Oxygen weighs 16.00. I'm dividing by its own mass. 0.4093 divided 12.01. This gives me here 0.03408. 0.04574 divided by 1.01. This gives me the hydrogen is 0.04529. And the 0.54496 divided by 16. I'm totally sloppy with safe face here just to make sure I don't have any rounding problems later on. These ones here, technically speaking, would actually be moles. I could actually at this point say my empirical formula is C, 0.03, hydrogen 0.04, oxygen 0.03. But what I'm going to do here is to start making them nice whole numbers. Divide out the smallest one here. The smallest one, not by much, but this time it's divided by 0.03406. So basically, the bottom one knocks to 1, 0.03408. This is just a smidgen over it. It's basically 1. And then we have 0.04529 divided by 0.03406. That gives me roughly 1.33. Here's where you use your judgment call here. I don't want to do crazy rounding in one chemical in case I scale the ratio. Well, this one here is a third. Let's actually scale everything up by 3. Let's make the carbon 3, the hydrogen 4, and the oxygen 3. And there we have our empirical formula, C3H4O3. That still is just a Lego block. That still could be a scaled down version of my real compound. Let's find our empirical mass. If this really were your compound, what's the molar mass of this compound? 3 times 12. I'll show you this what I'm typing in here. 3 times 12, 4 times 1.01, plus 3 times 16. Normally you don't show that work. 3 times 12.01 plus 4 times 1.01 plus 3 times 16. I'm getting a molar mass. Empirical unit is about 88. Again, this is all experimental. There's always going to be some sort of problems, sort of random errors, systematic errors, things like that. But roughly, you should be able to see, well, how many Lego pieces do I need to weigh 176? If you did a 176 divided by 8.07, you get 1.998, practically get about 2. So that means our molecular formula is actually going to be 2 times our Lego piece. Again, this is the one time you're actually allowed to actually change the subscripts. Our vitamin C is actually C6H8O6. In our organic chemistry part here, we're going to see that it isn't even detailed enough. This could still be branched in different ways. It can have rings in different fashions as well. We'll get a lot of isomers that may actually have this formula, but at least their molecular formula wise, at least the number of every element that we have wise, we have for every C6, there's exactly 8 H's, O6, these are the exact numbers. You're going to find that when you do that formula sort of number, if you did your molecular mass divided by empirical mass, this part here should at this point here be a whole number. It shouldn't be a 0.5 that you still need to scale up. Because your empirical mass here is your Lego piece, it should be a whole unit. Maybe it's 1 Lego piece, in this case it's 2. I've never seen this number get up to overly high, but it should be a whole number for you there. Right? So again, keep practicing your way through. That just sort of summarizes a little bit with how do you find the C's and H's through a combustion. We did the empirical formula that we had practiced, and a little bit towards the end with molecular formula. Right? Let me know if you have any questions. Thanks, guys.